the birth of time and the expansion of space. Before there were stars to shine or planets to orbit, there was a moment so brief and so overwhelming that our language struggles to contain it. This moment, often referred to as the birth of the universe, was not an explosion into space, but rather the sudden emergence of space itself. In a fraction of a second, the cosmos transitioned from a state of unimaginable density and heat into a swelling expanse that has been growing ever since. What emerged was not simply matter and energy, it was time itself, flowing for the first time, carrying every future moment within its current. The laws that govern our reality today were forged in that primal instant. Physicists describe this beginning through the framework of the Big Bang. Though the name itself can be misleading, it was not a bang in the conventional sense. It was a transformation from a state of no spatial dimensions and no temporal direction into a four-dimensional arena. 3 of space and 1 of time. In those first infinitesimal moments, the universe underwent what cosmologists call inflation, an extraordinarily rapid expansion where distances between points in space grew faster than light could travel. This was not a violation of Einstein's principles, for it was not matter moving through space, it was the fabric of space itself stretching. In the earliest breath of the cosmos, temperatures soared to levels beyond what any furnace or star could produce. Under such conditions, particles as we understand them today could not exist. Instead, there was a seething quantum field, a turbulent ocean of energy in which fleeting virtual particles emerged and vanished in constant chaotic rhythm. As expansion progressed and temperatures dropped, the first fundamental particles, quarks, electrons, neutrinos, solidified out of that energy field, each governed by the freshly minted rules of physics. This birth of time marked the beginning of cause and effect. Before this, before itself is meaningless, for time is not something that exists outside the universe, it is part of the universe. Asking what came before the Big Bang is like asking what is north of the North Pole. It is a question that assumes a framework which did not yet exist. Time, once begun, became the silent stage upon which all cosmic events would unfold. The ticking of its invisible clock defined sequences. Galaxies forming, stars igniting, planets coalescing, all built upon that first instant of temporal flow. The expansion of space has never ceased. Even now, more than 13 billion years later, galaxies drift apart as the cosmic fabric stretches. The rate of this expansion has not been constant. It slowed in the early universe as matter's gravity tugged inward, then billions of years later began to accelerate again due to a mysterious influence we call dark energy. This expansion is not into some empty void beyond the universe. It is the universe itself growing, carrying every atom, every star, and every moment with it. The birth of time and the expansion of space are inseparable in the story of existence. Together they form the foundation of the cosmic architecture. Without them, there would be no frame for matter to inhabit, no progression of events, no unfolding story to tell. They are the canvas and the clock, the silent partners to every motion and every thought that has ever existed. And as we move deeper into this journey, the question naturally arises: if space and time emerged together, what is their true nature? How can something intangible be stretched, curved, and shaped? To answer that, we must step into the realm where Einstein forever altered our understanding, into the idea that space and time are not separate entities at all, but one unified fabric. Space-time, due to the barren frost plains of Europa to the sunlit methane lakes of Titan, the hunt for life demands more than a search for water or organics. It demands an understanding of thermal gradients, the invisible temperatures, geology, and biology of alien worlds. A thermal gradient is not merely a line from hot to cold. It is a field of possibility, a delicate interplay between energy and matter that decides whether life might merely survive or truly thrive. On Earth, life clings to these gradients like ivy to a wall. In the abyssal darkness of hydrothermal vents, microbial colonies live on the razor's edge between searing vent fluid and frigid deep-sea currents. At the icy fringes of polar seas, single-celled organisms exploit the narrow band between freezing brine and slightly warmer water, eking out existence in conditions that would seem impossible to a surface-bound creature. Such examples prove a profound truth. Life is not simply a passenger in its environment. It is a strategist, positioning itself exactly where thermal conditions unlock the chemistry it needs. Beyond Earth, the implications are immense. Mars, though cold and arid today, once boasted river valleys, lake beds, and perhaps even shallow seas where thermal gradients existed between sunlit surfaces and subterranean aquifers. These gradients could have powered microbial metabolisms for eons before the planet's magnetic field faded and its atmosphere thinned. Even now, some planetary scientists suspect that briny pockets beneath the Martian regolith might host active gradients, small but sufficient for hardy extremophiles. Europa presents an even more tantalizing stage. Beneath its fractured ice shell lies an ocean deeper than all of Earth's combined, kept liquid not by sunlight, but by the kneading gravitational pull of Jupiter. That pull generates heat through tidal flexing, which in turn may create vents and plumes on the ocean floor, a recipe for thermal gradients, every bit as rich as those in Earth's hydrothermal ecosystems. If life lurks there, it likely follows the same rules, positioning itself precisely where energy meets nutrient flow, in the temperature zones where chemical reactions become possible. Thermal gradients do more than dictate habitability, they also guide exploration. Robotic missions must be designed to detect the smallest temperature changes, mapping zones where biology might exploit the available energy. Instruments capable of measuring micro-Kelvin variations become as important as cameras or spectrometers, because in alien oceans or buried aquifers, it is these slight differences, not vast extremes, that may reveal life's hiding places. In this way, the search for life is less like hunting for a single point, and more like reading the slope of a mountain. It is about tracing the incline where heat and cold meet in just the right balance, where chemistry shifts from sterile to fertile. And when we finally stand at the edge of such a gradient on another world, whether it is a geyser vent on Enceladus or a sunlit crater rim on Mars, we will not just be looking at a patch of alien terrain. We will be gazing into the very engine that may have powered the first spark of life there. The universe, vast and cold, is not uniform in its hostility. It is a patchwork quilt of extremes, stitched together by the narrow seams where life might gain a foothold. Thermal gradients are those seams, slender yet enduring, fragile yet powerful enough to alter the destiny of an entire planet. And so our journey to find life beyond Earth is not only a voyage across distance, but across temperature itself, chasing the subtle warmth in the cosmic cold, where existence may quietly bloom. The concept of thermal gradients and their relevance to habitability. Thermal gradients, the gradual change in temperature from one location to another, are more than just a feature of planetary physics. They are one of the silent architects of environmental diversity and, potentially, of life itself. In the vast landscapes of our own planet, these gradients are everywhere, from the steep temperature shifts around hydrothermal vents to the gradual cooling of the ocean as one dives into its depths, and from the sun-baked deserts that radiate heat into the night sky to the frigid polar ice caps. These differences in heat are not mere curiosities. They are engines of chemistry, circulation, and energy exchange. For life, temperature is not simply about warmth or coldness. It is about how heat influences molecular motion, reaction rates, and the stability of organic structures. In environments where thermal gradients are steep, boundaries are formed, interfaces where conditions change rapidly over a short distance. At these boundaries, unique chemical processes often emerge. For example, along the walls of a deep-sea vent, superheated, mineral-rich water meets near-freezing ocean current. The result is a zone brimming with reactive chemistry, where life exploits these stark differences to harvest energy. This principle is not confined to Earth. Across the solar system and beyond, scientists suspect that such gradients could mark the dividing lines between sterile and life-bearing environments. On Europa, the icy crust insulates a subsurface ocean from the frigid vacuum of space, while geothermal activity from the Moon's interior injects warmth into its depths. This creates a layered thermal profile, cold above, warm below, that could encourage nutrient cycling and localized ecosystems. Similarly, on Saturn's moon Enceladus, the dramatic difference between the freezing surface and the heated ocean floor may mirror the kind of environment in which Earth's earliest life once thrived. Thermal gradients also shape atmospheric processes. On planets like Mars, daytime heating and nighttime cooling create circulations that redistribute dust, moisture, and even trace gases that might indicate biological activity. On exoplanets, orbiting distant stars, gradients between day and night sides, especially for tidally locked worlds, could determine whether liquid water can exist at the boundary zones known as terminator regions. These twilight bands might harbor climates mild enough for habitability, despite the extreme conditions on either side. From a biochemical perspective, temperature controls not just the pace of reactions, but the very menu of chemistry available. Some reactions that build complex organic molecules only occur within specific thermal ranges, while others break down in excessive heat or freeze into inactivity in the cold. This is why the search for extraterrestrial life is so tightly linked to the mapping of thermal environments. Where there are gradients, there is the possibility of chemical disequilibrium, and disequilibrium is the playground of life. What makes thermal gradients so compelling is their dual role as both a challenge and an opportunity. Too steep a gradient can destroy fragile molecules, while too shallow a gradient may lack the energy flow to drive complexity. In this delicate balance lies the heart of planetary habitability studies, and it is why researchers meticulously model the temperature profiles of alien worlds. By tracing the invisible slopes of heat from surface to depth, from equator to pole, or from day to night, we draw a map of where in the cosmos conditions might tip in favor of biology. In the grand theater of the universe, time is not the fixed, unyielding ruler we often imagine. Instead, it bends, stretches, and contracts, molded by the invisible hands of gravity and motion. This strange truth lies at the heart of one of modern physics' most fascinating revelations: time dilation, the phenomenon that shows us that even something as fundamental as a second is not the same everywhere in the cosmos. The idea first emerged from Albert Einstein's theory of relativity in the early 20th century, a theory that forever shattered the Newtonian view of time as a universal constant. According to relativity, time is woven together with space into a single entity: space-time, where the ticking of a clock depends on both how fast it moves and the gravitational environment it inhabits. This means that two observers, separated by distance or velocity, can each measure a second differently, and both will be correct within their own frames of reference. There are two main ways that time dilation manifests. The first is gravitational time dilation, predicted by Einstein's general theory of relativity. Here, time runs more slowly in stronger gravitational fields. Imagine two identical clocks, one at the base of a massive mountain, the other at its peak. The clock closer to the center of Earth's gravity will tick ever so slightly more slowly than the one above, farther from the planet's pull. Although this difference is tiny, measured in billionths of a second over a lifetime, it becomes significant near extreme masses like neutron stars or black holes, where time for an outside observer could seem to almost stand still. The second is velocity-based time dilation, described by Einstein's special theory of relativity. As an object approaches the speed of light, time for it slows relative to stationary observers. This is not science fiction, but a measurable reality, confirmed by experiments with subatomic particles, called muons. These particles, created in the upper atmosphere, have lifespans so short they should decay before reaching the ground, yet they survive longer than expected because, from our perspective, their internal clocks are slowed by their immense speed. In human terms, the effect is negligible at everyday speeds, but it becomes monumental in the vastness of space travel. A spacecraft hurtling at a significant fraction of light speed could carry astronauts who, upon returning to Earth, would find that more years had passed for those who stayed behind than for themselves. This twin paradox, though a thought experiment at first, is a direct consequence of relativity and has been confirmed in principle by precision clock experiments on fast-moving satellites. The implications stretch beyond curiosity. They shape modern technology. Global Positioning System satellites orbit high above Earth in a weaker gravitational field and also move at high velocities relative to the surface. Engineers must account for both gravitational and velocity time dilation to keep GPS measurements accurate. Without these relativistic corrections, navigation errors would accumulate at astonishing rates, rendering the system useless in hours. Time dilation forces us to abandon the idea of a universal now. Instead, reality becomes a tapestry of local moments, each tied to its observer's position and motion. In the warped space-time near black holes, the effect becomes almost cinematic. An astronaut could, in theory, watch eons pass in the wider universe while experiencing only minutes. This idea, once purely theoretical, is now woven into astrophysical models of how matter behaves near event horizons where tidal forces stretch space and gravity slows the flow of time, almost to a halt. The elastic nature of seconds also prompts deep philosophical questions. If time is not fixed, then the concept of simultaneity, two events happening at the same time, loses meaning. The universe becomes less like a clock and more like a vast, shifting ocean, with each observer riding their own current through space-time. In the search for extraterrestrial life and the exploration of distant worlds, understanding time dilation becomes essential. Future interstellar voyages, if they reach relativistic speeds, will carry crews into futures they cannot entirely anticipate. The universe they return to may be older, changed in ways they could never witness along the way. This is both the beauty and the strangeness of the elastic second. It is a reminder that time is not a rigid cage, but a living dimension that bends to the forces of the cosmos. If you want, I can now extend this into a fully connected outline that fits seamlessly with the rest of your deep space documentary series. That way, it will feel like part of your ongoing cosmic journey narrative, rather than a standalone explanation. The curvature of space and the path of falling apples. In the quiet English countryside of the 17th century, a young Isaac Newton watched an apple fall from a tree. This moment, often romanticized, became the seed of a radical question. Was the same force pulling the apple downward also responsible for keeping the moon in its orbit around Earth? It was a simple act, an apple parting from its branch, but it opened a gateway to the idea that the heavens and the earth are governed by the same universal laws. Newton envisioned an invisible thread stretching from the apple to the moon, a gravitational pull that extended without limit into the cosmos. Yet, for over 2 centuries, gravity was understood as a mysterious force, acting across space, pulling masses toward each other, until a different mind came along to bend that very concept. Albert Einstein, in the early 20th century, dared to discard the picture of gravity as an invisible tug. In its place, he proposed a universe in which space and time were not fixed backdrops, but malleable, stretchable, and bendable fabrics. A single continuum called space-time. Gravity, in Einstein's view, was not a force at all, but the result of this fabric's curvature. The apple did not fall because Earth reached out to pull it. It fell because Earth's mass created a dimple in space-time, and the apple was simply following the curved path laid before it. Likewise, the moon was not held in place by an unseen tether, but was endlessly falling around Earth, trapped in the gentle warp of space-time geometry. The idea of curved space was radical. Imagine placing a heavy ball on a taut rubber sheet. The ball creates a dip, and any smaller object placed nearby rolls toward it, not because the ball pulls it, but because the surface itself guides its motion. This analogy, while imperfect, allowed the public to picture Einstein's general theory of relativity. Planets, stars, and even light itself move along curves carved into space-time by mass and energy. The bending of light around the Sun, observed during the solar eclipse of 1919, became the first spectacular proof that space could be warped, and that even photons, weightless yet energetic, obey the geometry of the universe. As telescopes and technology advanced, we discovered that this curvature was not a local phenomenon, but a fundamental property of the cosmos. The great arcs of galaxies, the spiraling dance of binary stars, and the pathways of spacecraft all follow the subtle, continuous folds of space-time. When a black hole forms, the curvature becomes so extreme that all paths lead inward, and not even light can escape. This is gravity at its most absolute, the warping of space to an infinite degree. Yet the apple's story, humble and earth-bound, is still at the heart of it all. The same mathematical framework that predicts the orbit of distant exoplanets also explains why you feel the weight of your body pressing against the ground. When astronauts float aboard the International Space Station, they are not free from gravity, but are in continuous free fall around Earth, just as the Moon is. The sensation of weightlessness is not the absence of gravity, but the experience of moving along space-time's curves without resistance. This understanding transforms our search for knowledge. We now recognize that mapping the curvature of space is essential not only for navigating spacecraft, but also for probing the universe's structure and destiny. Instruments like gravitational wave detectors, such as LIGO and Virgo, can sense ripples in spacetime caused by massive collisions billions of light years away, proving that the fabric Newton never imagined is dynamic, alive with motion. From a single falling apple to the grand sweep of cosmic arcs, the path is continuous. Newton's insight revealed a universal connection, and Einstein's vision showed that the stage on which the universe plays is not rigid, but shaped by its actors. Every orbit, every falling object, every beam of starlight is a silent testimony to the curvature of space. It is a reminder that the laws governing the cosmos are woven into the very geometry we inhabit, where an apple's gentle drop is kin to the orbit of worlds and the slow, endless spirals of galaxies. To run the earliest glimmers of human thought, the idea of a place where the very fabric of reality twists upon itself has fascinated and terrified in equal measure. Black holes, once only the subject of abstract mathematics and speculative philosophy, are now understood as real cosmic engines of gravity so extreme that they bend not only space but also the flow of time. They are not just voids, they are regions where the laws of physics as we know them approach their limits, where the smooth geometry of space-time collapses into a singularity, and where reality itself is reshaped in ways that defy ordinary experience. The story of black holes begins with Einstein's general theory of relativity, which revealed that space and time are not separate entities, but aspects of a single, interconnected fabric, space-time. Gravity, in this revolutionary view, is not an invisible force pulling objects together, as Newton described, but the warping of space-time caused by mass and energy. A star, a planet, or even your own body bends the space-time around it. The greater the mass, the greater the curvature. But in the case of a black hole, the curvature becomes so extreme that space-time folds in upon itself, creating a one-way boundary known as the event horizon. Inside this horizon, every path, whether taken by light or matter, curves inward, inevitably leading toward the singularity, a point of infinite density where the known laws of physics cease to function in their familiar form. From the outside, a black hole appears as a perfectly black sphere, yet it is more than an empty void. It is a gravitational well so deep that time itself flows differently near it. To a distant observer, a clock falling toward the event horizon appears to slow down, its ticks stretching longer and longer until they seem to freeze in place at the edge. But for the falling object itself, time feels normal. It is the outside universe that appears to accelerate toward an unimaginable future. This time distortion is not a trick of perception but a real consequence of space-time geometry. Near a black hole, the very definition of now becomes uncertain. Two observers in different gravitational environments will disagree about the sequence and duration of events. A second measured near the event horizon is not the same as a second far from it. This effect, gravitational time dilation, links black holes to the deepest questions about the nature of time, causality, and the universe's structure. Beyond their mind-bending impact on time, black holes are also architects of cosmic structure. The supermassive black holes at the centers of galaxies influence the motion of billions of stars, shaping the very architecture of galactic systems. Paradoxically, these regions of inescapable gravity can be sources of immense energy, powering quasars and relativistic jets that blaze across millions of light-years, visible from the farthest reaches of the cosmos. In these processes, black holes act as both destroyers and creators, consuming matter, yet driving the evolution of galaxies. At the quantum level, black holes raise even stranger possibilities. Stephen Hawking's groundbreaking work showed that black holes are not entirely black. They emit radiation due to quantum effects near the event horizon, a phenomenon now known as Hawking radiation. Over unimaginably long periods, this radiation could cause black holes to evaporate entirely, raising profound questions about the fate of the information that falls into them. Does the information vanish forever, violating the principles of quantum mechanics? Or is it somehow preserved in a way we have yet to understand? This information paradox remains one of the most compelling puzzles in modern physics. The distortion of time and space by black holes forces us to confront the boundaries of our theories and the limits of our perception. They are laboratories of the extreme, where relativity and quantum mechanics meet, often in tension, and where the very texture of reality is put to the test. To study a black hole is to glimpse the deep code of the universe, a code written not in lines of human language, but in the curves and folds of space-time itself. And yet, even with all we have learned, the full nature of black holes remains hidden behind their horizons. They are cosmic riddles, both terrifying and beautiful, reminding us that the universe is not a static clockwork, but a living, dynamic web of time and space, endlessly reshaping itself in ways our minds are only beginning to grasp. The arrow of time is not a physical arrow that one can hold. Rather, it is a metaphor that captures the asymmetry between the past and the future. And entropy is the driving force behind this asymmetry. In the mid-19th century, the Austrian physicist Ludwig Boltzmann provided a statistical foundation for this concept. He recognized that in any closed system, the number of possible disordered arrangements vastly outnumbers the ordered ones. Imagine shuffling a deck of cards. There's only one perfectly ordered arrangement, say all suits in sequence, but trillions of possible jumbled arrangements. When you shuffle, the probability overwhelmingly favors disorder, and that statistical tendency toward disorder is what we call an increase in entropy. ANN. In physical terms, the second law of thermodynamics states that in an isolated system, entropy will always stay the same or increase over time. It will never spontaneously decrease. This is why shattered glasses stay shattered, why smoke disperses in a room rather than reconcentrating in the corner, and why our universe appears to move from states of lower entropy to higher entropy. But here's the intriguing twist. The laws of physics at the microscopic level, Newtonian mechanics, electromagnetism, quantum theory, are time-symmetric. If you filmed the dance of individual particles and reversed the playback, the motion would still obey the same equations. Nature wouldn't know the difference. The arrow of time, then, emerges not from these fundamental laws, but from the initial conditions of the universe. Our cosmos began around 13.8 billion years ago in an incredibly hot, dense and low entropy state. That's counterintuitive, We often imagine the early universe as a chaotic fireball, but gravitationally speaking, it was astonishingly ordered. As the universe expanded, gravity pulled matter into clumps, forming stars, galaxies, and planets. At the same time, energy spread out, matter interacted, and entropy steadily increased. It is this growth of entropy, rooted in the improbable starting point of the cosmos, that defines the arrow of time we experience. Consider life itself. Every moment, our bodies burn fuel, convert it into usable energy, and expel waste heat into our environment. We are entropy machines, turning ordered chemical energy into less organized forms. Even our memories are shaped by entropy. We remember the past, but not the future, because in the past, the universe's configuration was more ordered, giving us a clear trail of causes leading to our present state. This also connects to the irreversible processes we witness in the grander scales. Stars burn their fuel, slowly increasing entropy until they die. Black holes swallow matter and radiate energy via Hawking radiation, converting the complexity of collapsed matter into a simpler bath of particles. Galaxies collide and merge, redistributing their stars into new arrangements. The cosmos is on a one-way path toward thermal equilibrium, where all energy is evenly spread and no further work can be done, a state known as heat death. Philosophically, the arrow of time forces us to confront deep questions. If the fundamental laws don't favor a direction, is time's flow merely a product of our universe's birth conditions? Could there exist other universes with no arrow of time at all, where past and future are indistinguishable? And if entropy is tied to our very perception of reality, does that mean that the passage of time itself is, in some sense, an illusion? While we may never see a broken glass leap back together, understanding entropy reveals that this irreversible journey is not just a human experience. It is written into the evolution of the cosmos itself. The arrow of time is the silent hand that shapes history, memory, decay, and transformation, carrying us from the ordered dawn of creation into the vast, entropic future. And so, every second we live is part of this universal story, a single step in an irreversible march that began with the birth of the universe and will continue until the last flicker of usable energy fades into the eternal stillness. In the heart of the universe's most extreme places, there exists a boundary where human understanding falters, where mathematics stumbles into infinities, and where the known laws of physics cease to operate. These are the space-time singularities, enigmatic points in the cosmos where density becomes infinite. Curvature of space is without limit, and time itself is stripped of meaning. They are not simply exotic features of the universe. They are the ultimate challenge to our deepest theories of reality. To understand what a singularity truly is, one must first appreciate the concept of space-time. Albert Einstein's theory of general relativity revealed that space and time are not rigid, immutable backdrops for the events of the cosmos. They are woven together into a flexible, dynamic fabric that bends, warps, and stretches under the influence of mass and energy. A massive star curves the space-time around it, guiding planets into orbits. The sun bends the path of starlight. And yet, under the right and extreme conditions, this curvature can become so intense that the rules break down entirely. The most famous example of a singularity hides within a black hole. When a massive star exhausts its nuclear fuel, gravity gains the upper hand. With no outward pressure from fusion to counteract it, the star collapses inward. If the star is heavy enough, no known force can stop this implosion. Matter is crushed to a point of zero volume and infinite density, a singularity, where gravitational pull is so overwhelming that even light cannot escape. At this heart of darkness, space-time is bent into a shape so extreme that it can no longer be described by Einstein's equations in their usual form. The mathematics predicts infinity, a signal that the theory is being pushed beyond its domain of validity. Yet singularities are not confined to the ends of massive stars. Cosmology teaches us that our entire universe began in a singularity of sorts, the Big Bang. According to standard models, if we wind the clock of cosmic expansion backward, we arrive at a state where the universe was compressed into an infinitely dense point. Space, time, matter, and energy all emerged from this mysterious beginning. The singularity at the birth of the universe is not surrounded by an event horizon like a black hole's core, but it shares the same troubling feature: the inability of current physical laws to describe what came before or what conditions were truly like at that moment. The problem is not just academic. Singularities are places where predictability ends. In every other region of space-time, general relativity allows us to forecast the future evolution of matter and energy given the present conditions. But at a singularity, the curvature becomes so great that time itself may cease to have meaning. Was there a before the Big Bang? What happens inside a black hole beyond the event horizon? Our equations refuse to tell us. This limitation has driven physicists toward the search for a deeper framework, one that unites general relativity with quantum mechanics into a full theory of quantum gravity. Quantum theory governs the microscopic realm where particles dance with uncertainty, while relativity governs the grand stage of planets, stars, and galaxies. Near a singularity, both realms collide. Space-time is curved to subatomic scales, and quantum effects cannot be ignored. Ideas like loop quantum gravity and string theory attempt to describe these extremes, suggesting that the infinite densities predicted by relativity may be replaced by finite, quantized structures of space and time. Perhaps, instead of a true point of infinite curvature, the core of a black hole might be a tangled discrete network of space-time atoms. The Penrose-Hawking singularity theorems, developed in the late 20th century, made a profound statement. Singularities are not rare oddities. They are inevitable outcomes of relativity given certain realistic conditions. These theorems shattered the hope that singularities might be avoided through exotic matter or special symmetries. Instead, they implied that space-time itself possesses built-in boundaries where our understanding will always require something beyond Einstein's vision. Singularities also raise deep philosophical questions. If the universe began in such a state, what determined the laws of physics that emerged? Are singularities portals to other universes, as some speculative models suggest? Or are they truly the ultimate dead ends of reality? Could information somehow survive passage through a singularity, as some quantum gravity proposals imply? Or is it obliterated forever? In the end, space-time singularities are not just problems for mathematicians. They are the edges of the map in humanity's exploration of the cosmos. They represent the points where nature withholds her final secrets, forcing us to invent new mathematics, new physics, and perhaps even new ways of thinking. Just as the horizon hides the vastness of the ocean beyond, the event horizon of a black hole conceals the strange and uncharted landscape of the singularity. We may not yet know what lies at the heart of these extremes, But one truth is certain: to solve the mystery of singularities is to take the next great leap in our understanding of the universe. They are the most dramatic reminders that, no matter how far science advances, there will always be frontiers where curiosity must lead the way, and where, for now, physics breaks in the realm of our everyday lives. Time feels steady and absolute. A second here is a second there, no matter who you are or where you stand. Yet, the deeper we look into the workings of the universe, the more this comforting certainty begins to dissolve. Modern physics tells us that time is not a universal metronome, ticking away identically for everyone. It is a pliable dimension woven into the very fabric of reality, and it can stretch, compress, or even appear to slow down. One of the most mind-bending illustrations of this truth is a thought experiment so famous that it has travelled from scientific papers into science fiction and philosophical debate: the twin paradox. The paradox begins with a simple premise. Imagine identical twins, born seconds apart, sharing the same childhood, the same rhythms of life. One twin, let's call her Anna, remains on Earth. The other, Elena, climbs aboard a spaceship capable of traveling at a significant fraction of the speed of light. Elena's ship embarks on a long journey to a distant star and then returns home. When she steps back onto Earth's soil, the two sisters embrace, only to discover something astonishing. Elena is younger than Anna, perhaps by years. Her clock, and even the biological processes of her body, have experienced less time. This outcome is not a fantasy. It is a direct consequence of Einstein's theory of special relativity. According to special relativity, the faster you move through space, the slower you move through time relative to someone who is stationary. This is time dilation, a real, measurable phenomenon confirmed in countless experiments. Muons, unstable subatomic particles, survive longer when traveling near light speed. Atomic clocks flown on aircraft or mounted on satellites tick at slightly different rates than identical clocks on Earth. And yet the paradox arises when we consider symmetry. From Elena's perspective, isn't Anna the one moving away at high speed? If motion is relative, shouldn't Anna be the younger one when they reunite? The resolution lies in the fact that their experiences are not truly symmetrical. Elena's journey involves acceleration and deceleration, turning the ship around to return home, while Anna remains in one continuous frame of reference on Earth. Acceleration changes the geometry of space-time for the traveler, breaking the symmetry and allowing special relativity to produce its startling result. The twin paradox also reminds us that clocks, whether mechanical, atomic, or biological, are not just human-made devices, but manifestations of the flow of time itself. In high-speed travel, all processes slow down in unison: the beating of a heart, the decay of atoms, the firing of neurons in the brain. For Elena, life aboard the ship feels perfectly normal. Seconds pass, hours pass, days pass, just as they always do. It is only when the twins are reunited and compare experiences that the vast gulf of accumulated difference becomes apparent. In the modern era, this is more than a theoretical curiosity. The Global Positioning System, GPS, must account for time dilation. Satellites orbiting Earth move fast enough and exist far enough from Earth's gravity that both special and general relativity affect their onboard clocks. Without precise relativistic corrections, GPS positions would drift by kilometers within a single day. But the twin paradox also brushes against deeper, more philosophical questions. If time itself is mutable, if it flows differently depending on motion and gravity, what does that mean for our understanding of now? Is the present truly universal, or does each observer carry their own private version of reality's clock? Einstein himself once remarked that the distinction between past, present, and future is a stubbornly persistent illusion. And so, the twin paradox stands as more than a puzzle. It is a window into a cosmos where time is not the master, but the dance partner of space, movement, and gravity. The story of Anna and Elena is not about defying the laws of physics, but about embracing them, seeing time not as rigid ruler, but as a stretchable thread in the fabric of space-time. In that realization lies one of the most humbling truths of modern science. The ticking of the clock is as much a journey as the path you travel. Gravitational time dilation near massive objects. Imagine standing at the foot of an enormous mountain, its sheer presence dominating the horizon. Now, stretch that idea beyond all earthly scales. Picture a star dense enough to pack the mass of our sun into the size of a city, or even a black hole whose gravitational field bends the very fabric of reality. In such environments, time itself does not flow as it does for you and me here on Earth. This phenomenon, known as gravitational time dilation, is one of the most fascinating predictions of Einstein's general theory of relativity. And it reveals that time is not a universal constant, but a flexible dimension, stretching and compressing depending on the strength of gravity. The concept begins with Einstein's radical insight. Gravity is not merely a force pulling objects together, as Isaac Newton described. Instead, it is the curvature of space-time caused by mass and energy. The more massive an object, the deeper the well it carves into the space-time fabric. Just as a marble rolling near the edge of a funnel slows as it climbs out. Light and even time itself are affected when they pass through these gravitational depressions. Near a massive object, clocks tick more slowly compared to those farther away. This is not a philosophical abstraction. It has been measured with extraordinary precision. In 1971, the Hafele-Keating experiment flew atomic clocks around the world on commercial airliners. They found that the clocks aboard the planes disagreed with identical clocks on the ground, both because of their motion, special relativity. Later, scientists conducted experiments using satellites and the ultra-precise Global Positioning System, GPS. Without correcting for gravitational time dilation, GPS signals would drift by about 38 microseconds per day, enough to throw off positions by kilometers within 24 hours. The deeper you descend into a gravitational well, the slower time runs relative to a distant observer. This effect becomes extreme near compact astrophysical objects. Around neutron stars, where gravity is billions of times stronger than Earth's, the time dilation is significant, but still survivable in principle. Near the event horizon of a black hole, however, the distortion is so intense that, from the perspective of an outside observer, time for someone falling in would appear to almost freeze. To the falling traveler, however, their own clock ticks normally. They simply notice that the rest of the universe seems to accelerate into the future. This strange warping of time even has real implications for how we think about the universe's history and future. In regions of extreme gravity, processes like decay, motion, and even thought occur more slowly relative to distant cosmic locations. The interplay between gravitational time dilation and cosmic expansion means that events near supermassive black holes may remain hidden to us for eons, perhaps forever. In a way, gravitational time dilation forces us to abandon the idea of one absolute, universal now. Time becomes personal, linked to position and gravitational influence. It tells us that the universe is not a static stage where events unfold, but an active, flexible tapestry, one that twists, stretches, and folds under the weight of stars, planets, and black holes. And so, next time you hear that a black hole distorts space, remember, it distorts time just as much. It is not just where you are that shapes your experience of reality, it is how deep you stand in the cosmic well of gravity, in the great theatre of the cosmos, where galaxies spin like vast celestial pinwheels and black holes loom like silent cosmic predators. There exists a number, unchanging, eternal, and absolute, that underpins the structure of reality itself. That number is the speed of light, 299,792,458 meters per second in the vacuum of space. Not merely a figure buried in the pages of physics textbooks, it is the ultimate speed limit of the universe, woven into the very geometry of space-time. To go faster is not just difficult, it is impossible, at least according to everything we know about the laws of nature. This cosmic limit was not always obvious. For centuries, light was believed to travel instantaneously, a perfect messenger without delay. The ancient Greeks debated its nature. Was it a particle, a wave? Was its speed infinite? It was not until the 17th century, when Danish astronomer Ole Romer studied the eclipses of Jupiter's moon Io, that the truth began to emerge. He discovered that light took time to cross the vast gulf between Jupiter and Earth, and thus it had a measurable speed. This was the first crack in the illusion of instantaneous vision. Centuries later, Albert Einstein would elevate this constant speed from a mere property of light to the bedrock principle of his theory of relativity. In Einstein's universe, the speed of light is not just a limit for photons, it is the limit for everything. No matter how much energy you pour into an object with mass, you can never accelerate it to or beyond the speed of light. Instead, as you approach it, your energy goes not into making you faster, but into distorting time and space around you. Time slows for you, distances warp, and the very fabric of reality bends to enforce this law. But why? The answer lies deep in the relationship between space and time themselves. In relativity, they are not separate arenas, but a single continuum. Space-time, and the speed of light, is the conversion factor that binds them together. It is the slope of the universe's ultimate ruler, the maximum rate at which cause can lead to effect. If information, matter, or energy could travel faster than light, causality would unravel. Events could happen before their causes, and the logical order of the cosmos would dissolve. This limitation shapes everything we see. It is the reason the sun's light takes 8 minutes to reach us, the reason we see distant galaxies as they were billions of years ago, and the reason there is a cosmic event horizon beyond which we can never know what lies. The speed of light is not merely a restriction, it is also a window into the past, a built-in time machine that lets us look back across cosmic history. The past says, I think the window looks back across cosmic history. Yet the speed of light is not always the speed at which light appears to travel. Through glass, water, or plasma, photons slow down as they interact with matter, but this is only an illusion. Their true limit in a vacuum remains untouched. Even in the strangest corners of physics, quantum entanglement, wormhole theories, or hypothetical tachyons, Nothing has been shown to transmit usable information faster than this constant. Still, humanity dreams of breaking this cosmic speed barrier. Concepts like warp drives and wormholes emerge not from defiance of Einstein's limit, but from attempts to bend the very fabric of space-time so that the limit no longer applies in the usual way. A warp drive, for example, would not move a ship faster than light through space. It would move space itself, carrying the ship along like a surfer riding a wave. These ideas remain speculative, but they show that even in obeying the limit, our imagination has found ways to dance around it. The speed of light is in the end the great enforcer of cosmic order. It is the heartbeat of the universe's design, the pace at which reality can change, the thread that ties space and time into a coherent whole. Without it, the laws of physics would fracture, the symmetry of nature would collapse, and the universe would lose its structure. To journey toward this limit is to brush against the edge of what is possible. And though we may never surpass it, we live in a cosmos where the chase itself has shaped civilizations, inspired exploration, and revealed the deepest truths of existence. The speed of light is not just a number. It is the whisper of the universe, telling us that even infinity has its boundaries. In the grand tapestry of the cosmos, distance is one of nature's most stubborn barriers. Stars shimmer in the night sky. Galaxies swirl in the far reaches of space, and yet most are so far away that even light, the fastest thing in the universe, would take millions or billions of years to reach them. For as long as humans have looked upward, we have been bound by a single truth: space is vast, and our journey through it is slow. But what if there was a way to bend the rules? To take a shortcut, not across the surface of the universe, but through its very fabric. This is the tantalizing idea of the wormhole. A bridge between two distant points in space-time, folding the cosmos upon itself like a sheet of paper and piercing it with a tunnel. The concept traces back to Albert Einstein's theory of general relativity, which revealed that space and time are not rigid backdrops, but flexible, dynamic entities, shaped by matter and energy. In 1935, Einstein, along with his colleague Nathan Rosen, stumbled upon a mathematical solution that seemed to describe a bridge between two regions of space-time. Known as the Einstein-Rosen bridge, it was unlike anything science had ever imagined. Not a simple passage through space, but a deep warping of reality itself. In this model, the universe could be connected in ways that defied intuition, linking two separate locations, perhaps even two separate universes, through a single, mysterious conduit. To visualize it, imagine space as a flat sheet of paper. Normally, if you wanted to travel from point A to point B, you would have to trace along the paper's surface, covering every inch of the distance in between. But if you fold a paper so that point A and point B touch, and then pierce a hole straight through, you have created a shortcut, a wormhole. For an object traveling through it, the journey could take moments, while in normal space, the same trip might take centuries. Yet wormholes are not merely science fiction fantasies. Their possibility emerges naturally from the mathematics of relativity. But there is a problem, perhaps several. The Einstein-Rosen bridge, as originally described, would collapse instantly if anything tried to pass through it. The tunnel would pinch shut before a single photon could cross. To hold a wormhole open, it would require something exotic. Matter with negative energy density, often referred to as exotic matter. Unlike normal matter, which has positive mass and energy, exotic matter would act like an anti-gravity force, pushing space apart instead of pulling it together. Without it, the walls of the wormhole would slam shut under the crushing force of gravity. In the 1980s, physicist Kip Thorne and his colleagues explored whether wormholes could, in theory, be stable enough for travel. Their work showed that if exotic matter existed, and in the right quantities, a traversable wormhole might not be ruled out by the laws of physics. This sparked a wave of fascination, not just in the scientific community, but in popular culture, inspiring books, films, and endless speculation about interstellar travel, time machines, and connections to parallel universes. The implications are staggering. A wormhole could allow not only faster-than-sight travel between distant stars, but potentially travel between different points in time. Because wormholes connect regions of space-time, moving one end of the wormhole at relativistic speeds could cause time to flow differently at each mouth, creating a time difference between them. Step into one end, and you could emerge not only in a distant galaxy, but in a different era, the past or the future. This is where the physics dances dangerously close to paradox, and where our understanding of causality, the sequence of cause and effect, is tested to its limits. Still, for all the mathematical beauty, there is a profound lack of evidence. No wormhole has ever been detected, and the energy requirements to build or sustain one are far beyond anything humanity can currently produce. The exotic matter needed remains hypothetical, and even if it exists, manipulating space-time on such a scale may forever remain in the realm of the impossible. Yet nature has a way of surprising us. Black holes, once thought to be purely theoretical, are now observed regularly. Gravitational waves, predicted for a century, have only recently been detected. If wormholes exist somewhere in the universe, perhaps hidden in the warped hearts of galaxies, then one day our instruments, or our descendants, might find them. In the end, the idea of wormholes speaks to something deeper than physics. It touches on humanity's restless urge to explore, to connect distant worlds, to transcend the boundaries of space and time. Whether they turn out to be real or not, wormholes remind us that the universe is not a static prison of empty void and unyielding laws. It is a living, flexible, mysterious thing, and perhaps, somewhere out there, it holds doors waiting to be opened. Temporal illusions, why the past feels real. Time is a strange thing. We live within its flow as naturally as a fish swims in water, yet the deeper we look, the less it behaves like the steady, unchanging river we think it is. To our senses, the past is gone, a shadow that exists only in memory. But why, then, does it feel so vividly alive? Why do moments long vanished sometimes feel closer than the present? This is the paradox of temporal illusion, the curious phenomenon where the mind treats the past as something tangible, almost as if it still exists somewhere, waiting for us to return. To understand why the past feels real, we must first face an unsettling truth. In the eyes of physics, time is not a flowing entity. Einstein's theory of relativity revealed that time is woven into the very fabric of the universe, space-time, and within this four-dimensional structure, all events, past, present, and future, are fixed like frames in a cosmic film reel. In such a universe, the moment you are reading this, the moment you were born, and the moment of humanity's distant future all exist together. The flow of time is not a universal reality, it is a property of consciousness. Our brains evolved not in the abstract world of space-time, but in the relentless cause and effect sequence of survival. The mind constructs time to keep track of events, to anticipate danger, to remember food sources, to recognize faces, to love and to grieve. Memory is its great tool, and memory is deceptive. Unlike a video recording, it is not a perfect playback. It is reconstructed each time, influenced by emotions, associations, and even the present moment itself. Yet when we recall a childhood scene, the smell of rain on dusty soil, the laughter of a friend, the rustle of leaves in the summer wind, the brain reactivates many of the same neural patterns that occurred when we first experienced it. In effect, we don't just remember the past, we partially relive it. But there is a deeper layer to this illusion, one tied to how time is structured in the universe itself. In the block universe interpretation of relativity, the past is not destroyed. It simply occupies a different location in space-time, like an old chapter in a book you can no longer turn back to. We can't physically revisit it, but its existence is just as real as this present moment. When you stand under the night sky, the starlight you see left its source hundreds, thousands, even millions of years ago. In a sense, you are looking directly into the past, not just imagining it, but actually perceiving ancient moments frozen in light. This connection between memory, perception, and the physical reality of space-time creates the strange sensation that the past exists somewhere, as if we could step through a hidden doorway and return to it. Science fiction often plays with this idea: time machines, portals, wormholes. But the laws of physics resist such journeys. The arrow of time, dictated by entropy, pushes us forward relentlessly. The universe's tendency toward disorder ensures that the past remains ordered, stable, and unreachable, while the present dissolves into the growing sea of what has already happened. Yet emotionally, the past never fully lets go of us. Neurological studies show that recalling a memory can activate the same emotional circuits as the original event. This is why grief can feel fresh after decades, why joy from an old victory can still make us smile, and why heartbreak can return with the same sting as the first day it happened. The mind does not differentiate between then and now as sharply as physics does. In the theatre of our consciousness, the past can walk the same stage as the present. And so we are left with a truth both haunting and beautiful. The past feels real because, in a very real sense, it is. It lives in the architecture of space-time, in the patterns of light reaching our eyes from distant stars, and in the neural pathways of our minds. We cannot touch it, we cannot change it, but we can carry it. And in carrying it, we keep it alive. Perhaps that is the deepest temporal illusion of all, that what is gone can never return, when in fact it has never truly left. Time before the Big Bang, does it exist? The question of whether time existed before the Big Bang is one of the deepest and most perplexing puzzles in cosmology, blending physics, philosophy, and even metaphysics. To answer it, we must confront what the Big Bang actually was, not as a fiery explosion in empty space, but as the origin of the very fabric of space and time itself. According to the standard cosmological model, the Big Bang was not an event within time, it was the birth of time. Before it, there was no before in the way we normally understand it, because before is a temporal concept that requires time to exist in the first place. Einstein's general theory of relativity, which describes gravity as the curvature of space-time, predicts that as we trace the history of the universe backward, the density, temperature, and curvature all increase until they approach infinity. At that singularity, about 13.8 billion years ago, Our current mathematical description of reality breaks down. Time, as defined by the ticking of clocks and the sequence of cause and effect, appears to reach a boundary. It is as if the river of time narrows to a point and simply stops. From this perspective, asking what happened before the Big Bang is akin to asking what is north of the North Pole. It may be a meaningless question in our current framework. Yet, physics does not stop at boundaries, it seeks to cross them. Quantum cosmology, which attempts to unite quantum mechanics with general relativity, opens possibilities for what before could mean. Some theories suggest that time is not fundamental but emergent, arising from deeper, timeless laws of physics. In such scenarios, the Big Bang may not have been the true beginning, but rather a transition, like ice melting into water. A change of state in a larger, eternal reality. One possibility is the cyclic universe model, in which the cosmos undergoes endless cycles of expansion and contraction, with each bang following a crunch. In this view, time stretches infinitely backward, and our Big Bang is just one chapter in an eternal book. Another is the quantum bounce, suggested by loop quantum gravity, in which the universe did not emerge from nothing but rebounded from a prior contracting state, avoiding the singularity entirely. There is also the multiverse hypothesis, where our Big Bang is one bubble among countless others forming in an eternal inflationary background, a vast and timeless sea spawning universes endlessly. Even more radical ideas come from Stephen Hawking's no boundary proposal, which imagines time, near the Big Bang, behaving like space. It has no edge, no before, but is finite in extent. In this model, the question, what happened before time, becomes unnecessary. Because time didn't begin in a singular moment, it smoothly emerged from a kind of timeless quantum realm. The difficulty in answering this question lies in our human perspective. We experience time as a flowing river, always moving from past to future. We intuitively imagine that every event has something before it. But the universe may not conform to this intuition. Time could be an artifact of the universe's expansion, a feature that simply did not exist in any meaningful sense before our cosmos took shape. And so, the existence or non-existence of time before the Big Bang is not only a scientific puzzle but also a philosophical one. If time began with the universe, then the Big Bang was the ultimate origin, the boundary beyond which before has no meaning. If time existed beforehand, then the Big Bang might have been just one moment in an infinite, possibly cyclical cosmic story. Until we have a full theory of quantum gravity, we are left with possibilities, not certainties. What is certain is that in exploring this question, we are forced to confront the limits of our understanding, and perhaps even the limits of what can be known. Whether time began 13.8 billion years ago or stretches eternally into the past, the mystery invites us to keep asking, keep imagining, and keep pushing the boundaries of physics toward the edges of reality itself. The clash of giants, general relativity versus quantum mechanics. General relativity, formulated by Albert Einstein in 1915, describes space and time not as separate entities, but as a unified four-dimensional space-time. It is a flexible, dynamic fabric that bends and curves in the presence of mass and energy. In Einstein's view, gravity is not a force in the traditional Newtonian sense, it is the result of space-time curvature. Massive objects like stars and planets warp space-time, and objects follow the curves of this geometry. Quantum mechanics, developed between 1900 and the 1920s, focuses on the smallest scales of reality, the behavior of particles, energy, and fields at atomic and subatomic levels. It replaces certainty with probability, describing particles as wave-like entities governed by the uncertainty principle and probabilistic wave functions. Both theories have been tested countless times. Both work extraordinarily well within their domains, but they refuse to play nicely together. General relativity works flawlessly at large scales. Planets, galaxies, the universe itself, while quantum mechanics dominates at the atomic and subatomic scales. Yet, at the extreme boundaries of nature, such as inside black holes, or during the first fraction of a second after the Big Bang, both theories are required at once, and there they clash. Mathematically, when we try to apply quantum principles to space-time as described by general relativity, the equations spiral into infinities, nonsensical, unphysical results. This failure has driven physicists for decades to search for a quantum theory of gravity, a framework that describes gravity in the same probabilistic, quantized way that we describe the other forces of nature. The loop quantum gravity vision. Loop quantum gravity takes a refreshingly grounded approach. Instead of embedding our universe into higher dimensions or postulating exotic strings vibrating in unseen spaces, LQG works directly with what general relativity already gives us, the dynamic fabric of space-time, and applies quantum principles to it. The key insight of LQG is that if matter is quantized and energy is quantized, perhaps space itself is quantized. The continuous geometric fields of general relativity, when viewed through a quantum lens, break down into a network of finite, indivisible chunks. Discrete atoms of space. In this view, geometry itself becomes granular. Just as photons are the smallest quanta of light, these space atoms are the smallest possible units of area and volume. Below this scale, the very concept of space ceases to exist in the way we understand it. Spin networks, the atoms of space. In the mathematics of LQG, these discrete chunks of space are described by something called a spin network. Developed originally by Roger Penrose in the 1970s and later incorporated into LQG by Carlo Rovelli, Lee Smolin, and others, a spin network is not a structure sitting inside space. Imagine a vast interconnected web. The edges of the web carry values known as spins, which are related to the quantum numbers familiar from particle physics. The nodes, where the edges meet, represent elementary volumes of space. The edges themselves represent quantized areas, and their intersection patterns encode the curvature and connectivity of space. In other words, space is not a backdrop against which events happen. It emerges from the relationships and connections in this network. The web is constantly evolving, changing its shape and structure, giving rise to the dynamic geometry we experience as space-time. Tidal galaxies, twisted by gravity. In the vast cold architecture of the universe, galaxies are not the isolated islands we once believed them to be. They are wanderers in a sea of gravitational tides, drawn toward one another in slow, majestic dances that can last for billions of years. These cosmic encounters leave behind breathtaking relics, tidal galaxies contorted and stretched by the overwhelming force of gravity. These galactic forms are not merely visual spectacles. They are deep records of the universe's dynamism, violence, and continuous creation. Tidal galaxies emerge from gravitational interactions between massive galaxies. Unlike the serene spirals we often imagine when thinking of galaxies, tidal galaxies wear the scars of cosmic battles. When two or more galaxies come close enough, their mutual gravitational pull begins to tug at their outer stars, clouds of gas and dark matter. These tugs do not happen instantly, but unfold over millions or even billions of years. Stars are flung into tidal tails, enormous, thread-like streams of stellar material, stretching across intergalactic space, sometimes forming arcs that span hundreds of thousands of light-years. The first clues to the existence of tidal galaxies came in the mid-20th century with improvements in photographic plate sensitivity and telescope optics. Astronomers began noticing peculiar galaxy shapes, twisted, stretched, and bent structures that defied classical spiral or elliptical categorization. The classic pair, known as the antennae galaxies, is one of the most iconic examples. Located in the constellation Corvus, this duo appears to be locked in a slow magmatic collision, their stars flung outward in brilliant arcs that resemble insect antennae. These trails are not static. They evolve, merge, and sometimes collapse into new structures altogether. But the wonder of tidal galaxies lies not only in their forms, but in what they teach us about galactic evolution. These interactions often trigger immense waves of star formation. As gas clouds are compressed by gravitational forces and shock waves, they collapse under their own weight, igniting bursts of newborn stars. Some of the most vibrant stellar nurseries ever observed are found in the heart of tidal interactions. Yet this creation often comes with destruction. Galactic cores may be destabilized. Supermassive black holes can begin to consume more matter, and entire structural features of galaxies may be torn apart, never to reform. From a scientific perspective, tidal galaxies offer an exceptional opportunity to study the role of gravity not just as a force of attraction, but as an agent of transformation. Simulations and models of galaxy collisions have revealed that these events are not rare. In fact, the Milky Way itself is not immune. Our home galaxy is on a collision course with the Andromeda Galaxy, a celestial ballet expected to begin in earnest in about 4 billion years. Already, satellite galaxies like the Large and Small Magellanic Clouds are stirring up tidal features in the Milky Way's halo, subtle arcs of stars and gas that hint at the beginning of a grand merger. These future tidal features will reshape the Milky Way, giving rise to yet another generation of twisted, luminous structures. Even the dark matter component of galaxies plays a crucial role in shaping tidal galaxies. Though invisible, dark matter contributes the majority of mass in most galaxies, forming vast halos that extend far beyond the visible stars. During a galactic encounter, these dark matter halos interact gravitationally as well, guiding the overall shape and trajectory of the tidal structures. Without dark matter, tidal interactions would look radically different, less organized, less elongated, and lacking the coherence we observe. Thus, tidal galaxies serve as a silent testimony to the dark scaffolding of the universe. Beyond their scientific importance, tidal galaxies also carry philosophical weight. They remind us that beauty often comes from struggle, and that creation is frequently born from conflict. They are visual metaphors for resilience and transformation, telling a story of cosmic resilience and rebirth. Through their tortured shapes, we see the universe not as a static machine, but as a living, evolving organism, one that tears itself apart and builds anew, cycle after cycle. Yet even these grand tidal features are temporary. Over vast stretches of time, the dramatic tails and bridges will fade. Stars will disperse into the larger galactic halos, and the memory of the collision will be lost, save for the newly merged galaxy at its center. These tidal ghosts are fleeting moments in the infinite film of cosmic evolution, captured only briefly by human eyes and instruments before they vanish into the background of space. As we observe these twisting galactic forms, we are not only looking outward, but forward. They are glimpses into the eventual fate of all galaxies, including our own. In their chaotic grace, tidal galaxies are both messengers of history and harbingers of what is to come. And with that glance into future galactic collisions and their inevitable consequences, we turn our attention to a stranger cosmic choreography, one that transcends even the most dramatic galaxy mergers. Next, we step into the realm of Outline 12, where we explore the bizarre and captivating world of ring galaxies, formed not by gradual spiral evolution, but by violent head-on collisions that send ripples through galactic disks like stones cast into a still. The Hercules Corona Borealis, Great Wall, the largest structure in the universe. As we leave behind the intricate gravitational dances that twist galaxies into tidal forms, our perspective must widen, not just across space, but across the very concept of scale itself. From the delicate, luminous threads spun by merging galaxies, we now move into a realm so vast, so profoundly immense, that it challenges the very boundaries of human comprehension. We arrive at what may be the largest known structure in the observable universe, the Hercules Corona Borealis Great Wall, a name as colossal as the cosmic giant it represents. Discovered in the early years of the 21st century, this immense superstructure came into view not through visible light or classical imaging, but through the detection of gamma-ray bursts, brief, high-energy flashes of radiation that typically signal the collapse of massive stars or the violent mergers of neutron stars. Astronomers analyzing data from deep sky surveys noticed a peculiar concentration of these bursts in a specific region of the sky, a statistical clustering too significant to be coincidental. The distribution pointed to a massive assembly of galaxies and galaxy clusters stretching across a truly unimaginable expanse, billions of light-years in length. The Hercules Corona Borealis Great Wall spans a region of sky that connects the constellations of Hercules and Corona Borealis, hence its name. The dimensions of this structure are staggering, over 10 billion light-years across at its greatest extent. To put this in context, our entire Milky Way galaxy is roughly 100,000 light-years in diameter. The Great Wall dwarfs not only our galaxy, but entire supercluster of galaxies, swallowing them like islands in a galactic ocean. It is not a wall in the traditional sense, but rather a vast web of gravitationally associated matter. Galaxies, dark matter, intergalactic gas, all interconnected in a filamentary structure that traces the skeleton of the cosmos. This raises a profound problem. According to the cosmological principle, the foundational idea in modern astrophysics that the universe is homogeneous and isotropic at sufficiently large scales, structures larger than about 1 billion light-years should not exist. The Hercules Corona Borealis Great Wall breaks that rule. It defies the expected limits of cosmic structure formation, posing a direct challenge to prevailing models of the early universe and the evolution of large-scale structures. If such a massive complex exists, how did it form within the age of the universe, and what unknown mechanisms might have guided its growth? Some scientists suggest that the wall could be a projection effect, or perhaps several smaller structures merely aligned along our line of sight. But deeper studies, cross-examined across wavelengths and time, continue to strengthen the case for its authenticity. If confirmed, the Hercules Corona Borealis Great Wall forces us to reimagine how matter organizes itself on the grandest scales. It may imply that the early universe had greater density fluctuations than our current models account for, or that gravitational clustering is more efficient across cosmic timescales than previously thought. This structure is part of a broader cosmic web, a vast interconnected lattice of filaments, voids, and nodes that define the very texture of the universe. Galaxies are not sprinkled evenly across space. Instead, they are found in thread-like formations, with vast empty regions in between. These threads converge in knots known as galaxy clusters, and the clusters themselves connect into larger assemblies called superclusters. The Great Wall may be the most extreme example of this arrangement, a kind of cosmic superhighway, where gravity has drawn together matter over distances that stagger the imagination. But the Great Wall is not just about scale. It also forces us to confront questions about the nature of the universe itself. If our cosmological assumptions are incorrect, what else might we be missing? Could there be even larger structures beyond our observational horizon? Or is the universe not as uniform as we once believed? The possibility that the cosmos harbors such immense, coherent formations adds fuel to discussions about anisotropies in the cosmic microwave background, alternative models of inflation, and even multiverse theories. Moreover, the Hercules Corona Borealis Great Wall reveals the extraordinary power of invisible forces in shaping the visible universe. Dark matter, unseen but gravitationally dominant, likely forms the backbone of this superstructure. Though we cannot see it directly, its influence is everywhere, guiding the motion of galaxies and sculpting the very architecture of space. In this way, the Great Wall becomes not only a structure of light and matter, but also a monument to the unseen, a cosmic fingerprint left by forces we still struggle to define. Even our ability to detect such a structure is a triumph of human ingenuity. The technology required to observe gamma-ray bursts across billions of light-years, to map their distribution, and to infer the existence of such a structure is itself the result of generations of scientific progress. From orbiting observatories to global data-sharing networks, the discovery of the Great Wall is a testament to how far humanity has reached into the deep night of space. And yet, as vast as it is, the Hercules Corona Borealis Great Wall may not be the final frontier of cosmic structure. As our instruments improve and our theories evolve, we may discover other megastructures, richer webs, longer filaments, deeper voids, stretching across space like neural pathways in a cosmic mind. And that idea, strange and poetic as it sounds, leads us to our next domain of wonder. For if the large-scale structure of the universe resembles a neural network, if it operates like an interconnected web, then it invites an even more profound question: could the universe itself be conscious? Or does it possess some deeper logic that echoes the patterns of thought, memory, and awareness? As we journey forward into Outline 13, we shall confront the enigmatic frontier of cosmic consciousness, where physics meets philosophy and where science begins to question the nature of perception, sentience, and the very architecture of reality itself. Starburst galaxies, galaxies on fire. From the colossal stillness of the Hercules Corona Borealis Great Wall, where cosmic architecture unfolds on a scale that mocks our sense of proportion, we now plunge back into more intimate, but no less dramatic, arenas of galactic life. If the Great Wall revealed the structure of the universe in skeletal form, then starburst galaxies represent its beating heart. Galaxies in a phase of violent, feverish transformation, igniting stars at a rate so furious that their entire evolutionary trajectory is altered. These are galaxies on fire, not with literal flames, but with the incandescent heat of explosive creation. A starburst galaxy is a galaxy caught in the throes of intense star formation, producing new stars at rates that can be dozens or even hundreds of times higher than those of ordinary galaxies. This frenzy of stellar birth is not a steady process, but a dramatic episode, a relatively short-lived surge in activity, often triggered by a specific catalyst. In astronomical terms, these starbursts are brief flashes of light and energy, often lasting only tens of millions of years, a blink of time compared to a galaxy's total lifespan, which typically stretches across billions of years. The triggers for starburst phases are as varied as they are violent. Galactic collisions, tidal interactions, and even internal gravitational instabilities can funnel vast quantities of cold gas into the central regions of a galaxy, collapsing it under its own weight. When this gas compresses rapidly, it creates the perfect conditions for star formation on a massive scale. Shock waves from previous supernovae, spiral density waves, or the gravitational tug of a passing satellite galaxy can all act as catalysts. The result is a firestorm of stellar birth, an astronomical version of a population explosion, where thousands of stars are born every year in tightly packed regions. One of the most studied starburst galaxies is Messier 82, also known as the Cigar Galaxy. Located in the constellation Ursa Major, it has become a cosmic laboratory for understanding the mechanics of starbursts. At its core, Messier 82 churns out stars at such an accelerated pace that its central regions glow with radiation, wind, and heat. Observations have revealed superwinds, enormous outflows of gas, driven by the combined energy of young stars, stellar winds, and supernovae blasting material out into intergalactic space. These superwinds can stretch for tens of thousands of light years, carrying not just gas but also heavy elements forged in the hearts of stars. The consequences of a starburst are profound and far-reaching. First, the sheer number of new stars changes the galaxy's structure and composition. Massive stars, which burn quickly and die young, explode as supernovae, enriching the surrounding space with metals like iron, calcium, and oxygen. These elements are essential for the formation of planets, moons, and life as we know it. In a sense, starburst galaxies are not only creating stars, but also seeding the future building blocks of life across the cosmos. Second, the energy released during a starburst can alter the galaxy's future. The supernovae and stellar winds inject so much momentum into the surrounding gas that it can halt further star formation or even eject gas entirely from the galaxy. This process, known as feedback, creates a self-regulating mechanism. A galaxy can only sustain a starburst for so long before it depletes its gas reserves or blows them out into space. Thus, the same process that ignites star birth can also extinguish it, leaving behind a quieter, more stable system. or sometimes a galaxy stripped of its fuel, unable to form stars for eons. There is also a deeper cosmological importance to these luminous bursts of creation. Starburst galaxies are more common in the early universe, where galaxy interactions and mergers were frequent. Studying them allows astronomers to peer backward in time, understanding how the first galaxies evolved, how heavy elements were distributed, and how large-scale structures formed. Starbursts may even be connected to the emergence of quasars, those brilliantly bright, black hole-powered beacons that shine across the deep past. In some cases, the same galactic collisions that trigger a starburst also feed the central black hole, setting off a chain reaction of cosmic activity that transforms the galaxy entirely. And beyond science, there is something undeniably poetic about starburst galaxies. They are the very embodiment of cosmic urgency, a blaze of life in the cold darkness of space. They speak to us about energy, transformation, and the delicate balance between growth and destruction. In their glowing cores and radiating winds, they offer a glimpse of the universe at its most active and alive, showing us that galaxies are not static ornaments, but dynamic entities shaped by pressure, momentum, and the relentless pulse of birth and death. Even their infrared and radio signatures tell a story. Much of their activity is obscured by dust, hidden from visible light, but revealed in other wavelengths. This makes starburst galaxies prime targets for observatories like the James Webb Space Telescope, which can peer into these dust-shrouded regions to reveal the tangled dance of stars being born amid clouds of gas. In doing so, we not only witness the inner workings of starburst galaxies, but also refine our understanding of stellar life cycles, galactic evolution, and the chemical heritage of the universe itself. And as we leave behind these luminous furnaces of creation, we are once again drawn toward mystery, toward that other side of galactic behavior that does not involve bursts of activity, but rather silence, decay, and disappearance. The universe, in all its grandeur, is not only a place of expansion and birth, it is also home to fading light, to celestial phenomena that whisper of ends rather than beginnings. And so, as we transition forward, we enter the domain of Outline 14, where we will explore the enigmatic nature of dark galaxies, galaxies without stars, invisible to ordinary observation, yet teeming with dark matter and hidden potential, veiled in the silence of the cosmic void, intergalactic stars, the loneliest wanderers in the cosmos. As we depart the heart of starburst galaxies, those luminous engines of creation, we are drawn toward a far more solitary and silent region of the universe. It is a realm not defined by frenetic birth or gravitational clashes, but by isolation, motion, and mystery. Here, between the vast gulfs that separate galaxies, travel stars that belong to no stellar city, no spiral arm, no galactic nucleus, these are the intergalactic stars, often called rogue stars, celestial exiles drifting through the dark vacuum between galaxies, untethered and alone. To understand the profound nature of these wandering stars, we must first grasp the environment they inhabit. The space between galaxies, known as the intergalactic medium, is vast and almost unimaginably empty. In these regions, the density of matter is so low that even light takes millions of years to travel between recognizable landmarks. Yet, scattered across this cosmic void are stars, that shine, burn, and age like their galactic cousins. But with one critical difference: they do so in isolation. The existence of intergalactic stars was first proposed as a theoretical consequence of galactic interactions. When two galaxies collide or pass closely by one another, the powerful gravitational forces involved can fling stars out of their home systems. These ejected stars are accelerated to such high velocities that they escaped the gravitational pull of both galaxies, hurtling outward into the intergalactic abyss. This process is not random chaos. It is governed by the elegant laws of orbital mechanics and the conservation of momentum. The most common mechanism involves gravitational slingshots, where stars near the core of a merging system are caught in the complex ballet of colliding tidal forces and flung outward with enough energy to break free from their galaxy's embrace. Observational confirmation came slowly, due in large part to the difficulty of detecting stars in deep space without the background glow of a galaxy. But with the advancement of deep field telescopes and instruments sensitive to faint light sources, astronomers began to identify luminous points floating between galaxies in clusters like Virgo and Coma. These stars, many of them red giants and supergiants, were too far from any galaxy to be bound to one, and their spatial distribution made clear that they were not mere statistical outliers. Instead, they represented a population of stars that had been torn from their homes and scattered across the intergalactic medium. The implications of these stars extend far beyond their unusual positions. Intergalactic stars act as tracers, natural probes that help map the gravitational and structural dynamics of galaxy clusters. Their distribution can reveal the history of past mergers, the mass distribution of dark matter halos, and the violent processes that have shaped the architecture of the universe. They are, in a sense, the fossils of cosmic violence, silent witnesses to events that unfolded over billions of years. Moreover, these stars challenge our understanding of stellar evolution in isolated environments. Most stars live within galaxies, where interstellar gas, magnetic fields, and stellar neighbors influence their formation, movement, and eventual death. But intergalactic stars exist largely without these interactions. They are solitary in the truest sense, evolving without the feedback mechanisms that govern galactic stellar populations. This isolation could lead to subtle differences in their lifespans, rotation rates, or end-of-life behavior. Differences that are still being studied and debated by astrophysicists. Some of these rogue stars are hypervelocity stars, traveling at speeds so extreme that they were likely ejected not just by merging galaxies, but by interactions with supermassive black holes. When a binary star system strays too close to such a black hole, tidal forces can rip it apart, flinging one star into intergalactic space while the other is devoured. These events produce some of the fastest objects in the universe and demonstrate the raw, destructive power of galactic core. Even more intriguing is the possibility that some intergalactic stars carry with them planetary systems, entire solar systems cast adrift in the cold dark. These potential rogue planets, orbiting stars far from any galaxy, might harbor moons, atmospheres, or even the elemental ingredients of life, all while flying through a universe that offers no nearby suns, no galactic context, and no celestial neighborhood. While purely speculative for now, the existence of such orphaned worlds poses deep philosophical questions about life's resilience and its possible emergence in environments we have barely begun to understand. Intergalactic stars also hint at the broader fate of galaxies and cosmic evolution. As galaxies merge and evolve, as stars are ejected and redistributed, the boundaries between what we call a galaxy and what lies outside it become blurred. Over cosmic timescales, stars leaking from galactic halos could form vast intergalactic stellar bridges, or clouds, challenging our definitions of structure and membership in the universe. The line between galaxy and intergalactic space is more porous than once believed. These lonely travelers, though few compared to the vast populations housed within galaxies, carry with them the stories of upheaval, acceleration, and exile. They shine against a backdrop of emptiness, reminding us that even in the most desolate reaches of space, stars still burn, life still pulses, and history continues to unfold. They offer us a unique lens, one not centered on belonging, but on freedom, motion, and the far-flung consequences of cosmic evolution. And just as these solitary stars illuminate the darkness between galaxies, they guide us toward another elusive phenomenon that inhabits the threshold of the observable and the theoretical. As we follow their trail further into the cosmos, we encounter not visible stars or known matter, but something far more mysterious and paradoxical: galactic systems that seem to contain no stars at all. In Outline 15, we delve into the strange, silent world of dark galaxies, invisible structures of hydrogen and dark matter that defy direct observation, yet may hold the keys to understanding how galaxies form, how matter assembles, and how much of the universe remains unseen. Dark galaxies, the invisible engines of the cosmos, as the glowing exiles of space. The intergalactic stars drift through the cosmic void in solitude. They reveal the aftermath of galactic upheaval and the dynamic violence that can unbind a star from its origin. But now we turn toward a stranger silence, not the quiet of isolation, but the absence of light itself. We descend into the shadows of the universe, seeking entities so elusive they cannot be seen. Yet their gravitational fingerprints mark their presence. These are the dark galaxies, structures composed almost entirely of invisible matter and gas, nearly devoid of stars and nearly undetectable by conventional observation. They are the missing pieces in our cosmic puzzle, the phantom frameworks on which the luminous universe is built. The notion of a galaxy without stars seems almost contradictory. For centuries, our understanding of galaxies was built around their stellar components: grand spirals of burning suns, ellipticals crowded with ancient stars, irregulars alive with star-forming clouds. Yet, as astronomical techniques improved and our surveys deepened, anomalies began to surface. Astronomers observed gravitational lensing where there should have been no visible mass. Hydrogen gas clouds swirled and rotated as though held together by unseen hands. These spectral structures hinted at massive collections of matter behaving like galaxies, but radiating little or no visible light. Thus emerged the theory of dark galaxies. Galaxies that possess the gravitational architecture of ordinary systems, but remain cloaked in obscurity. The primary signature of these entities lies in their hydrogen content. Neutral hydrogen emits radio waves at a specific wavelength, a spectral fingerprint that allows radio telescopes to detect and map vast clouds of interstellar gas. In regions where no stars are visible, but where this 21-centimeter line is strong and coherent, astronomers infer the presence of gas-rich galaxies that have failed to ignite into light. They rotate like galaxies, move like galaxies, and interact with other cosmic structures as galaxies do. Yet they shine with almost no visible light. These are the dark galaxies, whispering their existence through the quiet hum of hydrogen. One of the most compelling candidates for a dark galaxy is Virgo He21, a hydrogen-rich cloud located in the Virgo cluster. This object exhibits a strong rotational signature, implying a massive gravitational source. Yet deep optical surveys reveal no stars. Its motion and mass distribution suggest it is bound by an extensive dark matter halo, providing the gravitational cohesion necessary to keep it intact. It is not simply a fragment or remnant. It behaves like a galaxy, just one in which star formation has been suppressed or never initiated. This brings us to the deeper mystery. Why would a galaxy fail to form stars? The process of star formation depends on the cooling and collapse of gas within a gravitational well. But if the gas remains too warm, too diffuse, or too turbulent, it cannot contract into dense stellar cores. Feedback mechanisms from nearby galaxies, cosmic reionization in the early universe, or even internal gravitational instability could prevent star formation from taking hold. In this scenario, the dark galaxy becomes a kind of frozen potential, a massive reservoir of raw material that never crosses the threshold into illumination. Dark galaxies may be more than rare oddities. They could play a foundational role in galaxy formation itself. According to simulations of the early universe, galaxies formed through hierarchical assembly. Smaller structures merge to form larger ones, building complexity over time. Many of the earliest building blocks may have been dark or nearly dark, aggregating gas and dark matter before conditions became right for star formation. In this sense, modern dark galaxies may be evolutionary holdouts, primordial remnants from an earlier cosmic era caught in suspended development. Moreover, these elusive structures challenge our methods of cosmic census. The luminous universe, the stars, the galaxies, the glowing nebulae, is only a partial map. If dark galaxies are numerous, then we may be drastically underestimating the number and distribution of galactic systems. Their presence may explain discrepancies in mass calculations for galaxy clusters, or the mismatch between observed and predicted satellite galaxies in galactic halos. The so-called missing satellites problem. The lack of visible small galaxies around the Milky Way compared to what models predict could be partly resolved by accounting for non-luminous satellites that lurk just beyond the reach of our optical instruments. Detecting dark galaxies requires more than visual scrutiny. It demands multi-wavelength observations, gravitational studies, and careful modeling of gas dynamics. Instruments like the Arecibo Observatory, before its collapse, and current arrays such as ALMA and the upcoming Square Kilometre Array are critical to mapping these spectral shadows. As technology advances, we edge closer to illuminating what has long remained in the dark. There is a poetic irony to these entities. In a universe defined by light, it is the dark that often holds the most mass, the most influence. Dark matter itself, which constitutes the majority of galactic mass, is invisible. And now, with dark galaxies, we face the reality that entire systems of stars may be ghostly in nature, not in the process of fading, but never having truly ignited. These silent structures, unlit but gravitationally active, are reminders that the cosmos is not limited to what we see. They demand humility in our exploration, a recognition that our senses and tools, powerful as they are, reveal only a narrow slice of reality. The fabric of the universe is woven with both presence and absence, and the dance between the seen and the unseen may be the key to understanding it all. And as we leave these hidden galactic phantoms behind, we are led to yet another cosmic mystery, one where light, rather than being absent, is bent, magnified, and sometimes multiplied. In Outline 16, we step into the extraordinary phenomenon of gravitational lensing, where massive objects warp the very shape of space itself, turning galaxies into cosmic lenses and revealing the deepest secrets of the universe through the curvature of light, galaxy clusters, and the cosmic web, the architecture of the universe. Emerging from the veiled domain of dark galaxies, those elusive, lightless scaffolds of cosmic evolution, we are now drawn outward into the grand design that holds the entire universe together, where dark galaxies represent the hidden microstructures of the cosmos, galaxy clusters and the cosmic web define its overarching form. This is the vast and dynamic framework upon which all matter, light, and movement are suspended. It is a structure that does not merely house galaxies, it organizes them, sculpts their motion, and dictates the paths of energy and time itself. Galaxy clusters are the largest gravitationally bound systems in the universe. They are not mere groupings of a few galaxies drifting near one another, but enormous congregations, often comprising hundreds or even thousands of galaxies, locked in orbit around a common center of mass. Bound by gravity, these clusters are enveloped in colossal halos of dark matter, threaded with streams of hot ionized gas and permeated by magnetic fields and relic radiation. They are not tranquil places. Within them, galaxies crash, merge, and strip one another of gas. These clusters are battlegrounds of evolution, where the past and future of galaxies are written in gravitational dynamics. Each galaxy within a cluster is like a single spark in a roaring bonfire. Some glide quietly through the intracluster medium, while others interact violently, distorted by tides and ram pressure, triggering bursts of star formation or extinguishing it entirely. The environment of a cluster can radically reshape a galaxy's fate. It can strip away the cold gas needed for star formation, turning spirals into ellipticals and quenching galactic youth in favor of ancient starlight. The physics at play within clusters is governed not just by gravity, but by the interplay of radiation, shockwaves, plasma turbulence, and dark matter flows. These vast regions are the laboratories of cosmic behavior. Yet even these massive clusters are not isolated. They are connected to one another through a deeper, more intricate structure, the cosmic web. This is the true shape of the universe, invisible to the naked eye, yet revealed through careful observation of galaxy distribution, gravitational lensing, and the behavior of intergalactic gas. The cosmic web is a filamentary network, a vast mesh composed of matter and energy stretching across billions of light years. Along its strands lie galaxies and clusters, while the spaces between, the voids, are eerily empty, almost devoid of galaxies altogether. This web-like structure emerged from the early fluctuations in the density of matter just after the Big Bang. As the universe expanded and cooled, gravity began to amplify these initial imperfections. Dense regions drew in more matter, growing into the filaments we see today. Simulations of cosmic evolution show this process with breathtaking clarity. We looked from a nearly uniform cloud of hydrogen and helium, the universe self-organized into a textured lattice, a universal framework of filaments and nodes where matter congregates and galaxies ignite. The intersections of these filaments are where galaxy clusters reside, often forming superclusters, mighty agglomerations of matter stretching hundreds of millions of light years across. One of the most massive such structures known is the Lagniaphite supercluster, the home region of our own Milky Way. This immense gravitational basin spans over 500 million light-years and contains more than 100,000 galaxies, all flowing toward a common gravitational center. Lagniaphite is not a separate entity from the cosmic web. It is a node within it, a swelling along a cosmic artery, part of a vast cosmic river flowing through intergalactic space. The cosmic web also provides crucial insight into the nature of dark matter and dark energy. Since most of the universe's matter is invisible, we detect it not by light, but by its influence. The shape and density of the web, the motion of galaxies along its threads, and the warping of light by its gravitational wells all serve as indirect measures of the dark scaffolding that underpins reality. Even the temperature and density of the intergalactic medium within the web's filaments tell stories of heating by quasars, shocks from gravitational collapse, and the chemical enrichment of the universe over time. In recent years, the cosmic web has come into sharper focus, thanks to sky mapping surveys like the Sloan Digital Sky Survey and space-based observations from missions such as Planck. These projects have charted the positions and motions of millions of galaxies, revealing not a random distribution but a finely structured tapestry. The universe is not chaotic. It is exquisitely ordered at scales that dwarf comprehension. Beyond its scientific significance, the cosmic web evokes a profound philosophical perspective. Its resemblance to neural networks has led some thinkers to draw analogies between the structure of the cosmos and the structure of the mind. While this comparison is speculative and metaphorical, it forces us to ask, is the universe a machine, a living system, or something beyond all categories we understand? The web, with its connections, flows, and branching logic, appears not as a random scattering of matter, but as a deliberate unfolding, an expression of laws deeper than we yet know. And so, from the dark, starless realms of invisible galaxies to the glowing strands of the cosmic web, we come to see the universe as a layered creation, each level of structure building upon the last. It is not a place of mere explosions and voids, but of patterns and architectures, woven with energy and time, forged by the gravity of what is seen and the mystery of what is not. Now, as we trace the light and mass along these cosmic filaments, we are drawn toward yet another phenomenon that bends not just light, but space itself. In Outline 17, we journey into the realm of gravitational lensing, where matter becomes lens and space becomes canvas, revealing hidden galaxies, dark matter halos, and the warp geometry of the universe, the Helix Nebula, the eye of space. From the cosmic web's grand lattice work, threading galaxies, matter, and gravitational influence across billions of light years, we now focus our gaze on something far more intimate and haunting. We leave behind the enormous scales of interconnected filaments and plunge inward into the fate of a single star nearing the end of its life. What we find is a structure so delicately beautiful, so eerily symmetrical, that it has been called the Eye of Space. It is the Helix Nebula, a dying star's final exhalation frozen in luminous color, floating in the dark like a celestial iris, staring back at creation itself. Located in the constellation Aquarius, the Helix Nebula is among the closest planetary nebulae to Earth, offering an exquisite view of the stellar death process. But despite its name, A planetary nebula has nothing to do with planets. The term is a relic from early astronomers who, peering through primitive telescopes, saw round, disc-like shapes resembling distant planets. In truth, a planetary nebula represents one of the final stages in the evolution of a medium-sized star, like our own Sun, and the helix is one of the most well-studied and vivid examples of this cosmic transformation. The story of the Helix Nebula begins with a star that spent billions of years quietly fusing hydrogen into helium, radiating warmth and anchoring a solar system. Over time, as the hydrogen in its core was exhausted, the star grew unstable. Its outer layers expanded, becoming a red giant, and eventually gravity could no longer hold the envelope of gases against the pressure of radiation and stellar winds. The star shed these layers into space, forming expanding shells of gas and dust. What remained at its core was a white dwarf, an Earth-sized, incredibly dense stellar ember emitting intense ultraviolet radiation. That radiation illuminates the surrounding gas, making the Helix Nebula visible. The result is a glowing, multicolored structure shaped by fluid dynamics, magnetic fields, and centuries of stellar winds. The central region glows blue from ionized oxygen, while the outer edges burn red and orange from hydrogen and nitrogen. At the center of this stunning display, the white dwarf glimmers faintly, like the pupil of a ghostly eye. One of the most intriguing aspects of the Helix Nebula is its complex internal structure. What appears to be a simple ring is, in fact, a multi-layered cylinder, an illusion created by viewing a three-dimensional object from a single angle. Advanced imaging has revealed filamentary strands, comet-like knots, and radial spikes of material, all moving outward into interstellar space. These cometary knots, each larger than our solar system, are dense clumps of gas with long, trailing tails pointing away from the central white dwarf, shaped by photoionization and pressure gradients. Their existence was once unexpected and now remains a subject of deep astrophysical interest, as they may influence the final dispersal of the nebula. The helix is not just a pretty sight. It is a stellar autopsy, a snapshot of what will eventually happen to the Sun. Billions of years from now, our star will swell, shed its layers, and become a white dwarf surrounded by a planetary nebula. The Earth will likely be consumed or left as a dead, frozen relic drifting through space. The helix, then, offers not only beauty but foresight. It is a window into both our origin and our destiny. The carbon, oxygen, and heavier elements, scattered by the death of stars, like the one that formed the helix, are the very materials from which planets, oceans, and organic life arise. In its death, the star becomes a seedbed for new creation. Observations of the helix across different wavelengths, from visible light to infrared and X-ray, have revealed more than just glowing gas. They show shock fronts, interactions with the surrounding interstellar medium, and the cooling paths of matter as it disperses into the galaxy. This nebula is not an isolated event, but part of a continuous cycle in which stars are born, live, die, and return their elements to the universe, enriching future generations of stars and planets. There is something deeply human in the Helix Nebula's gaze. Across cultures and civilizations, eyes have symbolized awareness, vigilance, and the soul. To look upon the helix is to feel observed by the cosmos itself, as if the universe, through its processes of creation and dissolution, bears witness to its own unfolding. Its symmetry speaks to order within decay, structure within entropy, and its silent light traveling across hundreds of years to reach us, reminds us that we are part of this grand stellar continuum, that the atoms in our blood once burned in stars and will one day return to them. The helix is more than a structure. It is a metaphor made real by astrophysics. In it, we see the convergence of beauty and finality, science and symbolism. It teaches that the end is not an end at all, but a transformation, a dispersal of being into wider fields of possibility. And as we drift from the eye of space, we are once again invited to look further, not just with our instruments, but with our imaginations. From the disintegration of a single star, we now move to the bending of space itself. In Outline 18, we explore the astonishing realm of gravitational lensing, where gravity becomes not just a force, but a lens that reshapes light and behind the veil of distance and time.